So welcome everyone to the One World Combinatorics Onwards seminar. Our speaker today is Barry Greenfeld from the University of Washington, and he's going to speak to us about complexity of infinite words and of other things.
Okay, thank you very much. It's great to be here, great to speak here. Yeah, so I'll start to focus on complexity of infinite words. But if time permits, I will try to say a few words about connections and analogies with complexity and growth phenomena of other algebraic structures, somehow related to infinite words. All right, so I'm going to work over some finite alphabet. And as usual, we'll be looking at infinite words. And the complexity function of that infinite word is a natural valued function that counts how many subwords we have, distinct subwords we have of length n. Length and subwords of W. And what I will be looking at in this talk is a so-called the inverse problem of complexity functions, namely which functions, which natural valued functions occur as complexity functions of some infinite words. Now, the importance of this question is it's a little bit like the inverse Galois problem. Right? What is the importance? That if you find obstacles or features of complexity functions, there should be some good reasons for that, and these reasons should reveal something hopefully fundamental on the combinatorics of infinite words. All right, so let's start with some easy facts about complexity functions. Some easy facts. Well, they are always non-decreasing. In fact, most of the time they're increasing, unless the complexity function is eventually constant, which happens if W is eventually periodic. So if we look at the possible growth rates, we have let's say this is n, this is the complexity function. Then we have the constant or eventually constant functions. That's on one side. And then if you're not eventually periodic, if your word is not eventually periodic, then your complexity function is at least n plus 1. And this threshold is best possible, and of course is very important, and corresponds to Sturman sequences. And on the other extreme, we have complexity functions of exponential growth. So if W is a word over sigma, let's say sigma has d letters, then the complexity function is obviously bounded from above by d to the n. Of course, you can achieve this upper bound. Another easy fact is that we'll call some multiplicativity. So P of n plus m is at most P of n times P of m. And the reason for that is that if you take any length n plus m word, it is uniquely determined by its length n prefix and length m suffix. All right, so these are easy facts, some harder facts. So the first hard fact is a theorem of Cassin, 96, that if the complexity function is linear, then the discrete derivative, that's p of n minus p of n minus 1, is constant. So that's interesting. So you cannot have phenomena like, piecewise linear function with these gaps being unbounded. That's impossible. The next fact is so hard that I don't even think it's known. I mean, it was open for a while. I'm not sure. Maybe someone in the audience knows the state of the art better. I think it's a question if the complexity function is at most n to the alpha, or some real number alpha, must its discrete derivative be at most n to the alpha minus 1. I don't know if it's been resolved since then. All right, so and there are many other interesting results on possible behavior of complexity functions, about the density of gaps in the discrete derivative, many other things that unfortunately I cannot cover. But yet there have been also many, let's say, constructive or positive results, realizing many functions as possible complexity functions of infinite words. So many interesting realization, let's call them, the realization constructions, realization results. Again, to mention only a few, because the list is too long and there are so many beautiful results. So just to mention a selected sample of the flurry of results. So you can arrange your complexity function to be asymptotically n to the 1 plus alpha and log beta, say beta 1, then some iterated logarithm if you want. You can do that finitely many times. For any real numbers, alpha, beta 1, beta 2, alpha needs to be positive. This is seen and discuss. In the exponential realm, you can attain any growth exponent, or more dynamically any topological entropy. So you can have the entropy topological entropy is given by the limit 1 over n log the n, can be an arbitrary positive real number, even within pretty nice sequences, strictly ergodic sequences. It goes back to Riedenberger, as far as I know. And then there are many nice realization results in the intermediate realm, intermediate growth functions, which are faster than polynomial functions, but slower than exponential functions. So, for example, it is possible to construct infinite words with log complexity being asymptotically any sufficiently nice, keep it vague on purpose, sufficiently nice function. This is again Cassin 20 years ago. So, for example, you can take your complexity function to be something like exponential of n to the alpha for some real number alpha, and of course many other more complicated examples. Now, the perspective that I'm going to take when looking at this inverse problem of complexity functions is borrowed from large-scale geometry. So I want to introduce the notion of asymptotic equivalence in the sense of large-scale geometry. And so, given two non-decreasing, let's say, decreasing functions, natural valued functions. Let us say that f is asymptotically dominated by g. Denote it this way. If for some constants, you can take them to be the same constant if you want, and every large enough input, f of n is dominated by g up to some constant scale of the input and the output. And we say that f is asymptotically equivalent to g if f is both dominated by and dominates g asymptotically. So in a compact form, if there exists some positive c, such that for every large enough n, let's say f is at most c, g, c, n, and at least 1 over c, g, 1 over c. Now this concept is crucial in large-scale geometry, since many times we're interested in metric spaces up to quasi-isometry, not isometry. For example, when we look at Cayley graphs of groups, if we take a finitely generated group, say finitely generated group, and we look at its Cayley graph with respect to some generating set, let's say S1, or let's say two generating sets, S1 and S2, then the corresponding Cayley graphs would not be isometric. They're definitely quasi-isometric. And so when we want to measure the order of magnitude of growth of the group, growth of gamma is defined as the number of the volume of the ball of radius n centered at the origin in the Cayley graph of gamma. But of course, numerically, this depends on the choice of the Cayley graph, which in turn depends on the choice of generating set. If you replace a generating set, since we want a genuine invariant of the group and not something that depends on the choice of generating set, you must consider this, so this is well defined, only up to asymptotic equivalence. In the context of complexity functions, we can think of asymptotic equivalence of complexity functions as sort of identifying weighted complexity functions of the same infinite word, weighted complexity. So for this sake, it will be easier to consider a slight variation of the complexity function. Let's consider its global counting function. So we can look at P, capital P of n. Let's say that's the number of length most n subwords W, and then suppose we assign some weights, some positive real numbers as weights, or let's say costs, for the letters of the alphabet. So each one of them has some different cost, positive real number, and then we can consider the weighted complexity function, or the weighted global complexity function, counting subwords W of total weight or total cost at most n. And then if you take the same word and consider different weights or different costs, then the resulting weighted complexity, global complexity functions are going to be only asymptotically equivalent to each other. And now another reason, maybe the best reason to consider, maybe not quite this asymptotic equivalence relation, but at least consider complexity functions not numerically, but up to some equivalence relation, is that if you look at them in the sort of correct category, you look at them as the dynamical systems, symbolic dynamical systems that they generate, then the complexity function is not well defined. So if you take an infinite word and you look at its subshift, generate a subshift, that's the closure of the shift orbit, then it is definitely possible that you have different infinite words that generate different subshifts, which are isomorphic dynamical systems. So the correct term is conjugate. And then the complexity function is no longer an invariant of subshifts up to isomorphism, up to conjugacy. You need a slight finer equivalence relation, but still you need to consider some asymptotic equivalence notion rather than considering the actual values of the numerical values of your complexity function. All right, now with all of that in mind, I want to mention the first main result. So everything I'm saying here is a joint work with Gugu Moriera and Fim Zalmanov. 24. So it can be regarded as some kind of asymptotic solution of the inverse problem that I started with. Suppose f is increasing and submultiplicative. Right, so these are the necessary conditions we started with. Actually, maybe I should replace increasing by non-decreasing and increasing or constant. And mind you, submultiplicative means that f of n plus m is equal to f of n times f of m. It suffices to take to assume that f of 2n is at most f of n squared. Right, so suppose that f satisfies these necessary conditions, then there exists an infinite, in fact, even a recurrent infinite word, such that its complexity function is asymptotically equivalent to f. Right, so recurrent means that that's your infinite word. Every finite subword appears infinitely often. All right, I'd like to say a few words about the proof strategy, not a proof sketch, something even more vague. So, idea. So we're going to work over some finite alphabet, let's say 0, 1 to D, where 0 has a special role as a separator. So when you take more interesting words that involve the other digits, sometimes you want to sort of glue them together by sufficiently long intervals of zeros that sort of make sure that you don't create too many new words. And here's the idea. So let's say that for some good sequence of integers and k, when I say good, I mean log synthetic. So so each member of the sequence is greater than the previous one, but bounded by some fixed bounded constant times the previous one. So in our case, 8 and k. Suppose that for such a good sequence, for such a sufficiently dense sequence, we construct the following data. We construct a subset, a set of length nk words. Let's say its size is sk, some parameter sequence. So we control sk and nk. And then we can consider the union. Union and of course the union is not so much interesting. We need to look at the factorial language of the union. So the factorial closure, let's call it L, and that's a factorial language, factorial or hereditary language. So we take all possible finite subwords that appear in any of the words that appear in any of the XKs. And now, suppose that we can arrange the following things, the following conditions. So the first two conditions are more structural about the construction, and they have nothing to do with the desired function you're trying to realize. And the third condition sort of make sure that you take this new gadget, this new black box, and adjust it to mimic the behavior of your desired function f. So suppose that for every u and v in xk, u and then something v will appear as a subword in some, let's say, xl, or some l greater than k. Then it's not hard to see that this ensures that this factorial language can be viewed as a language, as a factorial language of some infinite word, and furthermore a recurrent word. So L comes from a recurrent word W. All right, that's great. And the second is that the complexity function of that infinite word is going to be more or less, I'm going to leave it vague in purpose because I want to talk more about the essence of things and not about the technical details, nk times sk. So the number of length nk words in your resulting infinite word is supposed to be up to some multiple constants, nk times sk. So what is the idea here? Why does it make sense to believe that this is possible? So what is nksk? That's the number of words we have. So sk is the number of words we have in xk. And suppose that for every word from xk, you pad it with zeros from the left and from the right, some number of zeros that is comparable with the length of the signal. nk, and these are also up to some bounded by some constant times nk. Then the number of sort of new words that you get in this way from each word in xk is about nk new words. Of course, they appear as subwords of some higher xk, say xk prime or xl, and this should be multiplied by the number of words we have. Sk is the number of words we have in xk, and so it's not so hard to arrange the right to left inequality. The left to right inequality is slightly more tricky and requires some additional say structure. Loosely speaking, to make sure that when you construct your new set of words, xk plus 1 or xk plus 2 and so on, you don't add too many new words, right? Well, it's easy to say, but basically the idea is to take existing words from previous stats, let's say xk, and then separate them by sufficiently many zeros. Sometimes it works, sometimes it's a bit more tricky. So these are the two, let's say, structural conditions. All right, very nice. But so far we said nothing about f, right? We need to somehow adjust this construction to give the desired, to realize a desired complexity function. And then suppose that we need to find many indices k such that f of nk is approximately nk times sk, the same nk sk that we saw here. And when I say many, again, I mean log synthetically many. And if we can arrange that, then for many indices, we'll have that f and k more or less agrees with pw of nk. And then it will follow from the definition of asymptotic equivalence that these functions are indeed asymptotically equivalent. So I will leave some of the technical details vague, but if you want to know what this means in practice, we'll call some such indices balanced. Say K is balanced. It means that NKSK, 2NKSK is at most F and K, and at least some constant 1/3 F, 1/3 NK. The actual numbers don't really matter. I mean, they matter for the construction, but for now they just think of them as some constants. But the way to read this inequality, this double inequality, is saying that F and K is more or less NKSK. So how do we ensure of these conditions? So in practice, most of the time, whatever that means, we take nk plus 1 to be some fixed multiple of nk. Let's say 3nk, or even let's say 2nk plus some delta. And we take, suppose we constructed a n1, s1, x1 all the way to nk, sk, xk, and now we need to construct nk plus 1, sk plus 1, xk plus 1. The question is how. And most of the time, we would like to take xk plus 1 to be a subset of the following collection. So we take an arbitrary word from xk. This costs us nk spots. Then we separate by many zeros. And then we put another word from xk. Of course, not all possible words. This will square the number of, like sk plus 1 be sk squared. Sometimes we won't take a fewer. So we take some subset of it, but we pick it in a smart enough way to ensure the first condition, the sort of recurrence condition. So this is also nk, and here we take either nk in sort of the normal step or this delta, and this delta needs to be not too small. I'll try to say a few words about it in a moment. And as long as we maintain this kind of behavior, and as I said, most of the time we can, this is more or less responsible for achieving 1 and 2, the structural conditions. All right, and then we need to ensure the third condition, as we call it, to find many balance indices. So now the game is chasing balance. How to find many balance indices. So I'm a bit cheating here because we don't really find balance indices. We control nk and sk, right, to some extent. And so the idea is to see how f behaves with respect to the construction so far, and then somehow, choose nk and sk within the limits of what the construction, the first and second conditions, allow you to make sure that you imitate the behavior of f. And there are 3 cases to consider. Proof is very algorithmic, and there's like a decision tree, and each step you have to decide in which one of these 3 cases you are. There are 3 cases, and you enter this decision. You enter any case with a balance index, and you hope to get out with another balance index. Sometimes you will, sometimes you have to wait a little bit, but after not too many steps, you will have a balance index, except for one subcase, but let's leave it for now. All right, so what are the 3 cases? The first case is what we call tame growth, and the superlatives refer to the function f. So when I say tame, I mean that f is fine. F is more or less aligned with our construction. In practice, I can write down the inequalities. They're written in terms of sk as a function of f and nk. So f3 and k over 6 and k, and greater than or equal to the square root of this number. So the 3 and the 6, again, they don't matter too much. What you should take from this inequality is that, that f and k, or f3 and k, is approximately nksk up to some linear factors, and up to a square root. Now the square root is crucial because we can somehow the difference between the square root of f3 and k divided by 6 and k and f3 and k divided by 6 and k is so that we can fix it with the next step. So this is a case where the construction, I would say, is pretty much aligned with us. So let's say this is nksk, and this is maybe nksk square, and our function f is somewhere here. This is f and k. And this is just illustration, so there are some constants here that I omit, but this is the idea. And yeah, in this case, within one step, you make sure that the k+1 is also balanced, and everything is good. Just proceed and go on with your life. The second case is more challenging. It's a case of rapid growth. Again, refers to the behavior of f. And yeah, so in terms of the conditions on nk and sk, it means that sk is smaller than square root. But since it's a condition on f, you should really think of it as saying that f is so fast that it's faster than nk times sk squared, right? Remember, we want f to be more or less comparable with nk and sk, or f of nk to be comparable with nk sk. Now it's so big that it's even bigger than nk sk squared. So this is us, nk squared, and f is just too fast. And this case is more challenging. So I didn't say, I mean, I mentioned before how normally we would like to proceed and construct xk+1. So in the first case, in the moderate or the tame growth case, we indeed take xk+1 as just a subset of, something from xk, 0, so this is nk, this is nk zeros, and then another thing from xk, and then we somehow enumerate the words and make sure that each one is preceded by some nice ones, so eventually we have recurrence. This strategy will no longer work if you want to fix the rapid growth case. And the reason is that f is just too fast. So loosely speaking, the idea is there is one technical step of one iteration of sort of preparation, construct enough new words, but then there is some subroutine of case 2 that constructs maybe k+1, k+2. When I say an index, I mean all of the data, nk+1, sk+1, xk+1, nk+2, sk+2, xk+2, and so on, until eventually you'll get a balanced index. And how do we plan to overcome f again? The idea, loosely speaking, is sort of shrinking. There's nothing we can do about the xk, it's just of length nk each time, or k plus I minus 1 if we want to construct the next step. But we want to shrink a little bit the window of zeros. So shrink it a little bit. Let's take it to be some delta k. So not a constant delta. Let's call it delta k. Now we have to be very careful. There are two contradicting forces here. On one hand, I would like to shrink the zeros so I can create more words. On the other hand, if I shrink the zeros too much, I can find myself violating the structural conditions. Structural conditions, the second one in particular, require that the P of nk will be more or less nksk. And as we said, this is much dependent on how spaced by gaps of zeros the existing words are. What turns out is that you need these delta k's. Let's say they're more or less nk divided by some sequence ak, turns out that what you need is that the series will be convergent. And so this is basically to ensure that when you get to the balanced index, it's not too late. Remember, we need the balanced indices to be log synthetic. We cannot just wait until we get a new balanced index. We need to get a new balanced index within some bounded multiple of the previous one. On the other hand, to still maintain the second structural condition, we need AK to be sub-exponential. Well, luckily, we went to school and we learned in calculus that we can take, for example, AK to be k squared, which is more or less what we take. All right, so this case is a bit more challenging, but eventually we'll get a new balanced index with one exception. And the only one exception is if the function is just consistently too fast to chase it, consistently too fast for the construction to overcome it, which means that the function is exponential. But this is fine because well, in real life, there are many exponential functions, right? 2 to the n is not the same as 3 to the n. But up to asymptotic equivalence, all exponential, at least multiplicative functions, are asymptotic equivalent to each other. So as far as I'm concerned, there's only one exponential function. And of course, we can realize recurrent, even infinitely uniformly recurrent words with exponential complexity. So asymptotic equivalence becomes finer for, I would say, for sub-exponential functions. And for polynomial functions, it basically agrees with the classical notion of equivalence up to constant multiplication. Now, the third case is, of course, f is tame, f is too fast. What happens if f is too slow? And I'm not saying much about this case. So, of course, it means that sk is greater than f3nk 6nk. But again, when we read it as a condition about f, it should say that f is just smaller than nksk, too small compared to nksk. This is nksk, and then f just becomes too slow. I would say this is maybe the most challenging case, and not say much about it. Somehow, so the idea is to construct new words in xk plus 1, xk plus 2, and so on, again, until eventually get a balanced index in a way that produces the fewest possible new words, but still, again, adhering the structural conditions 1 and 2. Very roughly, what we do is we place the existing words from the existing xk or xk plus I minus 1 on some kind of an imaginary circle, space with many zeros. And then the new words we take are going to be cyclic segments on this circle, longer and longer snakes. And so you basically there's an exponential decay of the number of new words, which also ensures that after finitely many times, we will exit this case, we'll get the balanced index, and then we can get back to this decision tree again. So this is the maybe overall framework for the construction, the proof of the theorem. Of course, there are many more details that I cannot get into. Since the theorem mentions recurrent words, it's kind of, I'm not sure if it's surprising, but it's not so clear if to begin with, given increasing some multiplicative function, well, maybe you can realize it has the complexity of an infinite word, but why a recurrent word? Well, somehow the recurrence condition is not too bad, right? It can be very weak in some sense. Just a new occurrence, nobody cares where. Things become much harder when you want to look at uniformly recurrent words. So what about uniformly recurrent words? So a word is uniformly recurrent if, well, recurrent means that every finite factor appears infinitely many times. Uniformly recurrent means that for every finite factor, there exists some let's say, some constant, depending on that subword, such that every long enough window, every window of length at least k, will contain at least one occurrence of that finite factor. That's a very strong notion of recurrence, and it dynamically corresponds to being a minimal subshift. So a subshift that contains no proper closed shift invariant subsets. And the first and the immediate and the fatal place where the previous strategy fails is, of course, that you cannot use the zero separator idea, right? If you have two long gaps of zeros, of course, this sharply contradicts the whole idea of being uniformly recurrent. And so we have a weaker result that does not quite realize a function up to asymptotic equivalence, but in the form that I'm going to bring, it's still, in some sense, best possible. So we also prove the following theorem. So suppose f is now I'll say just non-decreasing, but unbounded. So for example, it could be log n or something, and some multiplicative. Then there exists a uniformly recurrent word w such that the complexity of w is at least f, and at most f times some linear error factor. And if you think about it in the current form, the linear error factor is inevitable, because if f, you can, let's say you decrease it to something weaker and divide it by some increasing function, or n to the 1 minus epsilon, then you can take f to be n to the epsilon over 2. And by the gap of being either eventually constant or increasing, we said functions, complexity functions can be either bounded or at least n plus 1, you will not be able to realize any such word. So in some sense, this error factor is inevitable. So this is not a precise realization. It would be interesting to know if there is a complete analogous result to the previous one. That for every increasing some multiplicative function, you have a uniformly recurrent word realizing that complexity function up to asymptotic equivalence. I should say that this construction is very different from the previous one, and it's in some sense it's involved a development or modification, I would say, of a very neat and brilliant idea that was initiated by Bartoli and Combinatorics 10 years ago. Wanted to study growth functions of algebras. All right. Since I have a few more minutes, I'd like to say something about growth of algebraic structures, and hopefully about the connection between the two worlds. So, what is the fundamental problem of algebra, whatever that means? So many times in algebra, we want to classify algebraic structures, right? Classify groups, associative algebras, Lie algebras, algebraic varieties, representations of algebraic groups, whatever. But of course, this is a ridiculously broad problem. I mean, classify all groups. It's like asking a non-mathematician classify all things. But a remarkably successful sort of filtration of this problem is to ask for classification of algebraic structures of a given type of moderate growth, or tame growth, if you want. So we already mentioned before, actually, the notion of growth for a finitely generated group. So suppose that let's start with the case of groups. Suppose that we have a finitely generated group gamma, let's say generated by some finite set of generators. Its growth function, as we said, is well defined up to asymptotic equivalence, is a function that counts how many elements in gamma are products of at most n generators and their inverses, or as we said more geometrically, it's the volume growth of the radius n ball centered at the origin in the Cayley graph. So, for example, maybe the best example I know of a successful classification program under growth restrictions. It's a beautiful and highly influential theorem of Bohm. It says that groups of polynomial growth, polynomially bounded growth, are precisely the virtual linear groups. The right to the left implication was known before, but the more interesting part is the left to the right that gives a clean, algebraic, very rigid characterization of all finitely generated groups of moderate growth. All right. If you take, instead of a group, consider a finitely generated associative algebra. So if you don't work much with associative algebras, you can take, for example, the polynomial ring over some field with some finite number of commuting variables. Then, well, groups are more combinatorial or more geometric objects. You can count vertices in the Cayley graph, not so much for algebras, which are more linear objects. So instead of counting cardinalities, we want to count dimensions. And so the growth function is given by counting the dimension of the space spanned by all products of at most n generators. So just as a quick example, if you take the polynomial ring, commuting polynomial ring in the variables, then the generators are just the variables. And so how many linearly independent monomials of length n do we have with the variables? This should be n plus d minus 1, choose d minus 1. And if you want to, this is this example, if you want to count how many monomials you have of degree up to n, then it's this sum, which when d is fixed and n tends to infinity, behaves like n to the d. So we say that the growth function of a polynomial ring in the variables is n to the d. And as before, as in the case of complexity functions of words, you can ask the inverse problem of growth functions. You can ask them for groups, for algebras, for Lie algebras, name it. Which functions are just asymptotic equivalent to growth functions of associative algebras. It turns out that there are still necessary conditions as before. Well, f must be increasing or eventually constant. If the algebra is just a finite dimensional vector space, like a finite field extension, and f must be submultiplicative. However, these conditions, unlike the case of complexity functions of infinite words, these conditions are necessary but not sufficient. Not sufficient. To what extent are they sufficient? So there's a beautiful line of works on space of growth functions of algebras. Let me mention just a few. So already some 30 years ago, Belov, Gorsenko, and Latishev gave some very wild examples of growth functions of algebras. In, I think, 14, Bertoldi, Smoktanovich gave a clean and beautiful construction of algebras whose growth functions are squeezed or sandwiched between every increasing submultiplicative function up to some polynomial error factor. I think 3, maybe 2 or 3. then a few years ago, Bell and Zelmanov, I think 2021, maybe published in 21, gave a remarkable complete classification of all associative algebras, semigroups, and hereditary languages. It's a remarkable and beautiful, amazing result in terms of the discrete derivatives of these functions, of these root functions, and from which it also follows as a side consequence that you can realize an algebra between f and n times linear error factor. And there are some known bridges between infinite words and non-commutative algebras. So as consequences of the previous theorems that I mentioned, theorems on infinite words, we could prove the following, and with this I will finish. So suppose f is increasing submultiplicative, and then there exists a finitely generated prime associative algebra. Prime is it's a ring where the product of two non-zero ideals is non-zero, so it's some kind of a non-commutative counterpart of integral domain, such that the growth function of that algebra is asymptotically equivalent to f. And yeah, there's some issue with my tablet, but I'll just finish by that. And there is also a counterpart to the uniformly recurrent theorem. So there is some dictionary that translates let me just try to open it one more time. All right, sorry for that. All right, for some reason I cannot share my screen anymore, but yeah, so for any increasing submultiplicative function, you can find a finitely generated prime associative algebra whose growth function is f times this inevitable linear error factor that, as we mentioned, is needed, and as a translation of the theorem of uniformly recurrent words, for every, again, non-decreasing unbounded submultiplicative function, there exists a finitely generated even simple algebra, a simple associative algebra whose growth function is your desired function up to an at most quadratic error term. And just for context, I want to mention that the precise possible growth functions of groups, of finitely generated groups, is really far from being known. For example, the first example of a group of super polynomials of exponential growth was found only in the 80s. The first example of a precisely known growth function, which is intermediate, was found only in 2012, I think, by Bartoldi and Oechsler. And the first example of a simple group of sub-exponential growth, super polynomial sub-exponential growth, is only a recent work of a few years ago of Nekrashevich, and its precise growth function is still far from being done, as far as I know. All right, so that's all for today. Thank you very much.
Thank you very much. Does anyone have any questions? Oh yeah, Hajime.
So thank you for nice talk. And so you considered inverse problem of infinite language in the case where alphabet is arbitrarily so finite alphabet. So my question is about what happens if we fix alphabet, for example, in the case where sigma is 0, 1?
So you mean what if we restrict, let's say, to the binary alphabet?
Yes.
Yeah. So I think it's possible to compress the construction to a binary alphabet, and then instead of the digits, you might want to use something like 1 0 1 0 1 1 0 0, something like that. So I wouldn't be surprised if it's possible to somehow spread the digits in a finite alphabet, and everything should work fine because asymptotic equivalence still somehow you can convince asymptotic equivalence that finite words are actually letters. That's the strength of asymptotic equivalence. It's in a way it's thinking about costs. Declare that the cost of this new digit is whatever the length of the actual binary word is. So I totally believe it's possible to realize within binary alphabets.
Thank you.
Just simpler with longer ones.
Are there any other questions?
I have a question, actually. I don't know how to raise my hand on this thing, but
Oh no, go ahead.
yeah. Nice talk, Barry. Do you know, I guess the natural question is for uniformly recurrent words. Can you do similar construction in this case?
No, so as I said, the best we can do is for every non-decreasing unbounded submultiplicative function, we can find the uniformly recurrent word whose complexity is sandwiched between f and f times n. Now you cannot improve it unless you require that the function is not just non-decreasing but actually increasing. But I guess that's the bigger remaining question. Suppose f is increasing and submultiplicative, can we find a uniformly recurrent word whose complexity is asymptotic equivalent to f? That would be really nice because it will require a totally different strategy than the one that we utilized. Again,
Right.
the zero separator just kills any chance for being uniformly recurrent.
I see. Yeah, thanks.
So when you were working on this, were you originally trying to solve the problem for the associative algebras, or were you originally trying to just solve the problem for infinite words?
You caught me. So I come from the algebraic side, but I think it would be fair to say that Fim and I were more interested in the algebraic side, and we got together with Google and yeah.
Okay, fair enough. Does anyone else have a question for Barry?
Actually, I'll ask another question because Barry was mentioning Lie algebras, and Jeff and I have this Lie complexity, and I'm wondering maybe you can do something with your construction and looking at the Lie algebra associated to your monomial algebras. Say something about the getting growth functions in that case, do you think?
Right. So that's another very interesting question. So the classes of growth functions of associative algebras, that's the same as the class of growth functions of, for example, semigroups. And it contains the class, everything is up to asymptotic equivalence, contains the class of growth functions of groups, because for every group we can consider its group algebra, and is strictly contained class of growth functions of associative algebra is strictly contained in a class of growth functions of Lie algebras. So given every associative algebra, I can definitely realize its growth function as the growth function of some finitely generated Lie algebra. But of course, there are many new growth functions of Lie algebras that cannot possibly come from associative algebras. And the reason is that we don't have some multiplicativity anymore. So, for example, you can have functions of growth rate n to the 1.5 or something, which is impossible for algebras. So it would be really interesting to classify all growth functions of Lie algebras. And I think so there are always two parts, right? Finding the necessary conditions and then proving that they are sufficient. The only necessary conditions I know are being increasing sub-exponential. I guess you can say that fn plus 1 must be at most some constant times fn, but every increasing sub-exponential function is equivalent to such a function. When I say sub-exponential, I mean at most exponential. So I don't know if every increasing exponentially bounded function is equivalent to the growth function of some Lie algebra.
But maybe
I guess even the exponential realm is more interesting here, because I'm not sure. Yeah, it's kind of interesting.
But how about just to make it easier, do enveloping algebras? Then it should be relatively straightforward, right? You should have a gap between polynomial and e to the root n, and then maybe nothing else, maybe.
Right.
About increasing.
That's so. I mean, a completely plausible conjecture would be that at least using enveloping algebras, you can arrange for any, let's say, function greater than e to the square root of n. So symptotics of the partition function, which is bounded by exponential function, and increasing should be equivalent to the growth function of some enveloping algebra. Which would be nice because it's a domain, contains no zero divisors. But I don't know how to prove it. So the connection between growth of Lie algebras and their enveloping algebras is a bit cryptic. It's using
partition
series of magics. It's kind of hard to analyze, right?
Maybe.
Well, hard for me.
No, I'm sure.
So. Viktor Petrogradsky had some nice works on that, extending earlier works of Martha Smith. So he was interested in specific growth functions of the form something like e to the n to the alpha, or e to the n to the alpha divided by some iterated logarithm. But if we want to realize actually all, like literally all increasing submultiplicative, functions greater than e to the square root of n, I guess we need to just get maybe deeper into the analysis of these infinite products.
Yeah.
Maybe it's not bad.
Yeah, I'm not sure. Yeah. Thanks.
Thank you.
All right. Well, thanks a lot, Barry, for speaking in our seminar.
Thank you for having me.
We were very pleased to have you, and thanks everyone for coming today. Yeah, we'll see you all hopefully in 2 weeks for our next talk.